This is the pre-lab for experiment 23, where we're going to be determining the formula of a complex ion formed between iron 2 ions and the ligand phenanthralin. In this particular experiment, we're going to make a series of solutions with varying amounts of iron 2 ions and the ligand phenanthralin. And the first thing you're going to have to calculate is what the mole fraction is of phenanthralin in each of these different solutions, of which there are 12. If we do one of them as an example, let's take test tube number 1, solution number 1, where we're going to be mixing 4.50 milliliters of 3.0 times 10 to the minus fourth molar iron 2 with 0.50 milliliters of 3.0 times 10 to the minus fourth molar phenanthralin. What we need to calculate is the mole fraction of phenanthralin in that specific solution. Mole fraction is the moles of a particular component divided by the total moles in that solution. So we're going to need to calculate how many moles of iron 2 ions there are in the 4.50 milliliters we're using, how many moles of phenanthralin there are in the 0.50 milliliters that we're using, and then we'll calculate the mole fraction from those two numbers. So the first solution given here, you're going to do the calculation in box number 1. So first, for the iron 2 ions, to calculate the number of moles, we just multiply molarity times volume. So in this particular solution, we're going to wind up having 1.3 with a guard digit 5 times 10 to the minus 6th moles of iron 2 ions present. Doing the exact same thing for the phenanthralin, we're going to multiply its molarity by its volume, and this comes out 1.5 times 10 to the minus 7th moles. If you add those up, that's going to be the total number of moles it'll be in this particular solution, and then the mole fraction of phenanthralin is just going to be the moles of phenanthralin divided by the total. That total being 1.50 times 10 to the minus 6th. This mole fraction turns out to be 0.10. So when you go to your data table, you're going to be entering that as the mole fraction for the initial solution, tube 1, of 0.10. You're going to calculate the mole fraction for all 12 tubes exactly like we did there. Once you've done that, then we're going to wind up placing each of these tubes into a spectrometer at a specific wavelength and measuring their absorbances. So you'll determine during the experiment, much like we did back in earlier experiments 2 and 3 and 10 and 11, although those were on video, so this will be the first time you're doing it in person, you're going to determine what wavelength to use for this particular spectrophotometric analysis. I'm just making up a number here. Let's say we're going to use 510.0 nanometers as our wavelength. And then you're going to measure the absorbance of all 12 solutions shooting 510 nanometer light wavelengths through a cuvette containing these particular solutions, and you're going to have a variety of values. Now, what you're going to wind up noticing is that the absorbances will start to climb, and then at some point they'll start to decrease. So here, as we go from solutions 1 all the way up to solution 7, the absorbances are getting higher and higher. But when we get to test tube number 8 through test tube number 12, the absorbances go down. This is going to allow us to plot two linear regions when we graph absorbance versus mole fraction. And we're going to wind up doing something like this on Excel. So what you're going to have to do is look at all of your different absorbances and divide them into two fractions. The first fraction is where the absorbances are going up. The second fraction is when the absorbances are going down. And so in Excel, you're going to take all your mole fractions in which the absorbances are going up, and you're going to place those mole fractions in column A. I've made up some mole fractions here. Maybe they're right, maybe they're not, but 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. And then let's say the absorbances for those were 0.111, 0.222, etc. Notice the numbers are going up. Then the second fraction of my results in the experiment were solutions where the absorbances were going down. So I'm going to place those in columns C and D. So I've got my absorbances of 0.7, 0.8, and 0.9 in column C because the absorbances correlated to those, which are column D, go 0.678, 0.578, 0.478, they're going down. So when you put these two fractions of the data in separate columns like this, you can actually graph them separately. So we're going to graph the data in columns A and B. That's going to be a graph showing a linear relationship and with a positive slope because the absorbances are going up. So if you were to graph those first 6 points on Excel, the chart that would appear on your Excel spreadsheet would look something like this. You're able to have this particular graph display the line of best fit along with this equation, and you'll be doing that in Excel. In this case, the line of best fit looks like this, with the equation showing as y equals 1.11x. Something else you're going to do is you're going to want to extend or extrapolate the line past our final point being way over there on the right at 0.6 mole fraction. And you can do that in Excel. And if we do it here, you'll see that the blue dotted line continues past our last actual data point. That's called extrapolating. Now, we're going to now take the data in column C and D, and these are now the mole fraction solutions whose absorbances are going down, and we're going to graph those, and they're going to be graphed as a separate set of data. So when they get placed on here, you can see they're in a different color, and you can see that as the mole fraction goes up, the absorbance goes down. We'll once again have Excel determine the line of best fit, and it'll give us the equation for the line, which here y equals negative x plus 1.378, negative x because it's a negative slope. And what we want to do is we want to see where these two lines intersect. So we're going to ask Excel to take our orange line and extrapolate it before the first point we graphed, which was at 0.7 mole fraction, and it'll wind up going like this. The significance of this graph is that where those two lines intersect give us the optimal ratio of ligand to metal to actually create the complex ion. So graphically, you can just read down, and that looks like, I don't know what, maybe 0.65 or something like that. But to get an accurate reading, you determine that point or that x value by just setting the two equations equal to each other. So we set the two equations equal to each other. We'll say 1.11x equals negative x plus 1.378. And when you do that, you can solve for the x coordinate where these two lines intersect, and that's going to be our mole fraction. That's the optimal mole fraction of ligand to metal to actually create our complex ion. So let's say we actually solve those two simultaneous equations, and we wind up getting the mole fraction of 0.66. So what does this mean? This means in terms of moles, our complex ion is 66% ligand. 0.66 as a mole fraction is like 66%. So if the complex ion is 66% ligand, how much is it of metal? Well, it'd have to be 34%, right? 100 minus 66. So percents add up to 100, mole fractions add up to 1. So if we know that the mole fraction of the ligand is 0.66, the mole fraction of the metal has to be 1 minus 0.66 or 0.34. So this particular complex ion has 0.66 moles of ligand per every 0.34 moles of metal. And if you just divide those two numbers, you're going to get the ratio of the moles of ligand to metal. And when these are divided, that comes out to be 1.9. That means 1.9 moles of ligand to every 1 mole of metal. Now, you can't have 1.9 moles of a ligand, so that means there's some experimental error here, so you'll need to round that to the nearest integer. So essentially, this is telling us there's 2 moles of ligand to every 1 mole of metal, so the formula of the complex ion would have to be ML2. Now, in this particular experiment we're doing today, the structure of phenanthralin looks like this. It has 2 nitrogens with lone pairs located geometrically like this. That tells you something special about that ligand. And so when you're asked further questions about the coordination number of the metal in this complex, that'll actually be significant.